Okay, so this is going to be about position, velocity, acceleration right here. Um, I'm not going to work and like especially how integration works, like accumulating the functions too. So a few notes. This is reminders from when we did this before. Distance units are could be in miles, meters, centimeters, inches, and feet. Typically, we're talking about motion. Any kind of distance units works. Time units would maybe be seconds, minutes, hours, days, or distance over time. So, and if we're talking about position, it's going to, like, if this was meters and seconds was our positions and times, the units for position would be in like meters, velocity would be meters per second, and acceleration would be meters per second squared. So, like, your acceleration time is going to be the time unit squared on the bottom, and so on. So remember that just as a reminder for units, because that comes up in these kind of problems. And back in the day, we talked about deriving things. So the derivative position's velocity and derivative velocity's acceleration. So if we had this problem right here, where my position function was 3x squared plus 6x minus 5, and I asked you, okay, can you find those others? You would say, oh, velocity is just the derivative of that thing. It's going to be 6x plus 6. And then the acceleration would be the derivative of that. It's going to be 6. All right, we've done that before. We're probably pretty good with that. Now, let's talk. And there was a few terms we had in here, and I want to go over these kind of quickly here. Position function. Okay, position, the velocity, acceleration functions were right there. Sometimes we talk about the initial position. You might see this notation like S sub 0 if we use so position, like velocity is always V, acceleration is always A, but position could be like S. Sometimes I've seen D. Sometimes it's like X of T or Y of T if we're talking about position on an X or Y axis. Sometimes we talk about initial position, we go sub 0, and this is a very physics notation or velocity sub 0. That's the same thing as going V of 0. But you might see this sub 0 notation, especially in a physics type class. But I think in math, we typically write it like this, but these would be equivalent. They mean at time equals 0. The speed is going to be the absolute value of velocity. So the absolute value of v of t, we're talking speed. So going backwards would be negative velocity usually, but if we're talking backwards in speed, it's positive. Speed is absolute value. Displacement is like your net change. So from where you started to where you went, like how far did you go? So if you started at like at position 5 or whatever, and then at the end you were at you could be at negative, then you're at like position 10, you moved 5. Even if you went like backwards and forwards, it doesn't matter. It's like where you started versus where you ended, how your displacement. But now if we do total distance, we have to consider going backwards and forwards and add those up. So that's where like the sometimes absolute values come in, or you have to like do some math on if things are going forward and backward. So total distance traveled going in both directions. You have to add those times. So if you go back 5 and then you go forward 5, your distance you traveled was 10. But if you go back 5 and then forward 5, your displacement is 0 because you're back where you started. So a few things that have popped up, and I'm sure we're going to be doing those again. So let's say we calculus, we're doing integration. That's the point of this. If I'm doing it algebraically, we integrate acceleration and we get velocity. So I could say the integral of a of t is basically v of t, right? And so then the integral of v of t is s of t. And it's kind of, there's also this plus c part that we have to account for, but we're going to be doing those kind of things. So let's give an example right here. So let's say I started with 6 of t. Last time was just 6. And I said, okay, well, what's the v of t is going to be the integral of this thing. So that's going to be 6t squared over 2, which would be the same thing as 3t squared. But you also have to have a plus c. Now, you can't just say, oh, this is 6t squared, and then the integral of this thing would be 3t cubed over 3 and say it's, okay, t cubed. We have this plus c part. And you can't just say, oh, then this one's this plus c. No. Because the c here was already, we have to integrate that thing. You don't want to jump straight ahead like that, is what I'm trying to say. Whenever we integrate and try to find the velocity function, we want to solve for this c right here. Now, you'll be given, usually you're given in this case, some information that would tell you either the initial velocity or velocity at certain time on this function. In this case, let's say I gave you initial velocity of 2. When you have that, I don't need to write this as plus c. You can plug in 0 for time and 2 for this thing, but your c in this case is going to equal 2. So in the case of with our initial condition, I can actually say this is going to be 3t squared plus 2. So when I'm integrating to get position function, it's going to be t cubed plus 2t. Doing cursive t so it doesn't look like plus. But then we have a plus c here. Now, if I have to figure out that plus c, I have that initial, I don't have, let's say I don't have this initial condition. Let's say I have this right here. S of 3 is 12. So it's not my initial position is 12 because I'm getting not initial time. I have to plug both of those in. And how do you do that? Just plug in the math right here. So I would get, you say 12 is equal to 3 cubed plus 2 times 3 plus c. 3 cubes 27 plus 6 equals 12. That's going to be 33. And then you subtract 33 and you would get negative 21 is equal to c. I think that works out. So my actual function right here for position would be t cubed plus 2t minus 21. So algebraically, you have to account for the plus c's. That's sometimes the trick there. You're doing that algebraically. Now, graphically, I think is what this week's really going to focus on. And how do we interpret things graphically? So let's say I have this function right here. I just made this up. And I have a function of maybe velocity right here. And I just have some areas in the curve. So what if I asked you the integral from 0 to 5 of v of t dt? Okay, and that's going to be, just the area under the curve from 0 to 5. And we could say that's 14. Just this area right here. And if I asked you the area under the curve from 0 to 8 of v of t, okay, well, I have to add up both these areas. So this is 0, this is 8, so it's going to be 14 minus 2. It's going to be 12, okay. Now, if I asked you what's the area under the curve from 0 to like 7 of v of t, well, I know these are straight lines, but I'm not like, imagine these were just some weird curved lines. 7 would be like kind of like right here, right? How do I chop this up? This would be one of those cases where I don't have enough information. I couldn't tell you that. I could kind of estimate it and say, well, and look at that and maybe give it a rough estimate, but I'm not going to be able to give an exact answer because I don't have those specific areas in the curve under the curve. Now, all right, that's how you do those velocities. So my question would be, if I said this right here, let's go back to this one. The area in curve from 0 to 5 of v of t dt equals 14. What is this? I'm going to pause the video. What does that mean in context of those other words? Like, that's velocity. What does that mean about position? So if I had this is 14, let's say this is seconds of meters, this means I have my displacement. I have moved 14 meters in the positive direction at 5 seconds. This does not mean like if my position's at 14 because I have to account for what my initial position was. But it says, hey, I've moved that much time. And what if I asked the question? So that's how that kind of stuff works. We can look at it with graphs. Let's look at a few other things. Okay, I want to go to this worksheet right here, and we're doing this as a class. Everyone doing this, fill this in at home. I think this is really good, like notes and stuff. But let's look at this first part here. And we had this word bank, and what we know about those words. I'm going to give you some time. It's together. Let's see if we can fill this in. We filled this in, but that was kind of in that part before. Oh, that's probably not going to be too bad. Let's look at one of these problems below. We do this part 2 activity. So a particle moves along this axis. Now, this did not copy right. Not copy correctly. So a particle moves in the x-axis so that time t its position is given by x of t. Ignore the formatting's weird, but that's fine. And the velocity is given by v of t, okay? At time equals 2, the particle is located at x equals 5. And the following graph gives the velocity of the particle from 2 to 7. Match the numerical expressions to the verbal statements here. So, okay, so we're looking at this again with this graph. At time equals 2, and this is velocity. And then we're told at time equals 2, the particle is located at x equals 5. So I might even make a note here and say, hey, at x of 2 is equal to 5. All right, I might make those notes like that. And let's see which of these I can actually plug in. So the total distance traveled by the particle over the time from 2 to 7. Well, your total distance traveled, remember, this is like the absolute value of these movements. So, well, what's the area of these regions? I think we probably want to add these up. It looks like the area of this region is going to be -2. Adding up all this, the two triangles, that's -1, -1. The area of this region, what is the area of that region? It looks like it's going to be, it's a triangle, so it's going to be 1/2 times base times the base, which is going to be 3, times this height here is going to be 2. That's going to be an area of 3. I just want to do the math to make sure. So I put those in there. So if I want to get my total distance traveled, and I want to get my total distance traveled right here, I'm actually going to change my text to red. By the particle over this interval from 2 to 7. Actually, no, I'm just going to do it this way. I'd want to add this part. So I'm looking at a 3, and then plus this part. So my answer here would be A. It's a total distance traveled. So you'd have to treat these as positive or as absolute values. Now, your position of the particle at time equals 7 is based off your initial position plus the integral of the velocity. So I think we had that up there at the previous one. So my initial position is going to be this 5, and then plus the area under the curve of velocity from 2 to 7. So plus 3 minus 2. So my answer here would be C as that equation. Now, the change in position from 2 to 7. Your change in position is just the integral of this velocity, so it's going to be 3 minus 2, so that's going to be B. So there you see kind of those differences in displacement there. Feel free to stop me if I'm going too fast. Feel free to jump ahead if it's too slow. Let's look at this in a different way. Put some equations up here in case you wanted to see those. This one, particle moving along the x-axis, so at time t the position given by x of t and the velocity by v of t. So this is a completely different problem. Match the following integral expressions, like what do these actually mean? So, well, let's look at these. Again, I have another absolute value. Let's do what I know first. If I'm dealing with the absolute value, I'm dealing with my speed. That's the integral of speed, I know. Oops. But you're dealing with it from, when you integrate the absolute value of velocity, we're always also talking about distance traveled. So I'm looking for this keyword right here, distance traveled. It's a distance traveled from 2 to 7. You do absolute value velocity. When you're dealing with just integrating velocity right here, and it's not absolute value, we're talking about how much a displacement, or we can also call this a change of position. So a change of position right here going to be looking like this. So we're going to be looking like we're B right here. And so that would put this one. When you have x of 2, this is like your starting position plus the integral. Wait, these are ones that I'll just made above. This is going to be A right here. The position of the particle as time is 7 is your initial position plus this integral. Let's say I knew x of 2. All right? So let's look at part 4 below. I'm going to scroll on down. Part 4. Particle moves along the x-axis. So at time, it's given by x of t and the velocity v of t. At time equals 2, the particle is located at 1. The following table gives the velocity of the particle. So this is going to be, okay, with the table this time. At selected values from 2 to 7. If the integrals are approximated using a left Riemann sum, match the numerical expressions. Oh, yay, we got to do those again. So a few things in here I'd like writing down. At 2 is x equals 1, so I'm going to write down x of 2 is equal to -1. And then we got our, okay, so we're doing a left-hand Riemann sum here. I almost want to like graph these out. Like, let's say at time 2, 5, and 7, and it's not scaled right, but I don't care. My velocity here, and this is a velocity graph, is going to be at like -4. And then this one's going to be at like 6, at 5. And at 7, my velocity is going to be 3. I want to have that picture for me. So if you did a left-hand Riemann sum, what would these rectangles look like? Remember, left-hand Riemann sums are rectangles with the based off the left-hand side. So, and you're starting it on the left-hand side and going forward. So I'd actually have this. This is trippy. You're starting on the left, and you go to 5. You go down. This would be my first rectangle right there. And oh, that was perfect. No. Okay. And then this would be, let's see if I can just do straight lines here. So it'd actually be a left-hand rectangle based just looking like that. This one is going to be my next spot, and it's going to move over. It'd be a left-hand rectangle based off of that. Now, what's the area of each of those rectangles? Well, this length right here is 3, and this height here is -4. So my area for this one is -12. This length right here is 2, and this height's going to be 6. So this one's +12. That's kind of annoying that they're the same. But, oh, I guess that works out. Hey, weird. See what's going on here. So, okay, I wanted to draw that to show you what it looks like. Now we have some equations. Let's match them up. The total distance traveled by the particle over the interval. Remember, distance traveled is the absolute value of this. So it's going to be this +12 plus another +12. I'm going to be dealing with positive values here. That's going to be B. All right. Now your position of the particle at 7 is going to be based off this initial position. So I would say -1, which we wrote down right here. And then plus -12. So it'll be minus this 12. And then plus this other 12. Boom and boom. That's going to match up what A says right here. Left it as those, but okay. And your change of position is going to be how much you change from each of those. So it's going to be the -12 plus 12. It's going to be 0 from because you go backwards. Or you go back and then go back forward. So that would be C. And that's how you'd fill out those. It's useful. They asked you to do this, Riemann sums, they could come up. There's your picture. Questions on that? Or second to last. So we're gonna fill out this table here. So they got some integral expressions, and some of them look different, like this thingy or this thingy. Yeah. This is definitely good to keep these as a good note when we go back to this. The position of a particle moving on the x-axis is given by x of t, velocity is v of t, acceleration a of t. For each of the integral expressions, interpret its meaning by filling in the missing noun, appropriate units. What do they mean by noun here? Okay, so this is like, okay, units. Okay, we know what units are. We're dealing with, in this case, we're dealing with feet per second here. I'm actually going to highlight this myself. Actually, I should probably make a copy so I don't edit mine. I wonder if College Board's okay if I post this online, public video. I don't know. I don't think teachers. I don't know if teachers use these for assignments. It's not like the other secured stuff. All right, so I changed this so I could actually write in it without. Wait, why do I care? Okay. You don't like yellow? Deal. Okay. It's going to blind you. I'm going to do a very light orange. I just wanted to highlight this as a reminder to me that I'm going to be using feet per second right there. Or you can write this on the side. I don't care. So let's fill out this blocks. So how would I do this? I'm just going to use the stupid. Use my annotate mode. I don't want to use the other things. Never mind. All right, so I know I'm dealing with feet per second. So let's look at this box. I'm going to do this. I know it's feet per second. I'll remember that later. I'm moving it up. So your integral expression. We probably have to figure out the noun first. What is this thing? And, oh, you know how it says x prime of t? We haven't been dealing with this. We were dealing with v of t from 4 of 2, or from 2 to 4, right? But I can also write that as x prime of t. Like, that's legal to do. And you can have primes in those integrals. It'd be the same thing. So what is this going to be? This is our initial position plus the change of position. So what this is going to give me is, I would say, it's going to give me my position at x equals 2. So I might say, like, you know, position. Oh, it's going to be white. Oh, that's really gross. So position at x equals 4, not 2. So I'd say that would give me my position right there, because it's your initial position plus how much you moved from 2 to 4. Now, if it's dealing with position, my units are going to be in feet. And at 4 seconds. Cool. Moving on. What's this thing? This is just the, oh, but it's from 1 to 4. Okay. Not 2 to 4. It's a change in position of the particle, right? Now, what is the change of position in units? We're still position here. So I'm going to say it's still feet. And then it's, now what's the time? It's not, when we're talking about a change in something, we want to know the change in what interval it changed at. We don't know it and want to know it at a certain time. So it's going to, I'm going to say from 1 to 4 seconds. That works. Or from t equals 1 to 4, like they said below, that'd be fine. But that's what I go for your time. What's this one? So this is that average value of the function thing. So, you know, this part is when I do absolute value right here, this means the total displacement, the total amount I moved, right? And back and, or not, no, total distance traveled, right? But if I'm doing this, I'm trying to average it. So what would I actually say? I would say it's the average distance traveled. It's your average distance traveled every like second from 1 to 4. I would say it like that. Oh, that fit perfectly in that box. Smaller font. I could do. I can. I would call it that average distance traveled. So, or it's, would average distance traveled be accurate? Actually, would that be accurate? So this has nothing to do with position. I'm wrong. This is going to be your average speed, because the way the average value of a function works, when you want to average it, you want to average this thing inside. This is speed. So you're averaging this from 1 to 4. So this is going to give you your average speed between 1 and 4 seconds. And its time, it's going to be from 1 to 4. I can even just do domains from 1 to 4 because I'm lazy right now. There you go. Different than I was thinking first. I got tricked. Oh, this was a little different. So notice they flipped it here. X prime, V of t, same thing, but this is 4 to 2. And I have this initial position. This is also going to, it's similar to this one. So, but it's going to be the position at x equals 2. We're going backwards. What it's saying is, the way you can interpret this is at 4 seconds, but then what if we rewound it in time back to 2 seconds? And this will give us our position at time equals 2 seconds. It's a way to kind of go back in time. Like if I were to look back at these graphs, like I could have done this, like you said, oh, my position at x equals 8 is equal to 10. How do I use that to figure out my position at 5? You go backwards, right? You can go back in time. Um, yeah. So let's position at x equals 10. This next one. We just did this kind of up here. This is going to be, okay, this is integral of speed, right? And this gives you your distance traveled. So this is going to be distance traveled from 1 to 4 seconds. Your distance, position, this is going to be feet, and from 1 to 4 seconds. Your last one right up here. This gives you your average acceleration of the particle. Oh, I should have read that above. Now your average acceleration should be in feet per second squared, because we're talking acceleration still. And then we're still doing it from 1 to 4 seconds. Good table to read. Good activity. Questions on that before I move on? Okay, so this is going to be applying a few different things. We want to show, last part of this, show how this is equivalent to x of 2. So I want to go back to what does it mean to be, if I asked you the integral of a function, if I said integral of, let's say, x prime of t from 0 to 5, we can say this is x of t from 0 to 5. We do that bar thing, which is just, that means the top minus the bottom. So it's x of 5 minus x of 0. This is like the fundamental theorem of calculus, right? Or the definite integration. This is how it works. What if I interpret this, I look at this as definite integration to prove that this is equal to x of 2? Well, one thing I can say, I can rewrite this in a few different ways, is this equation right here. I'm going to rewrite this as from 4 to 2 of x prime of t dt. Okay, good. Same thing as v of t. So I have x of 4 plus that. Well, this part would just be the same thing as x of t from 4 to 2, which I can write as x of 2 minus, yeah, you can write this. Yeah, you can all write this in notes and stuff or print out or whatever. Minus x of 4. So now that I've done this, these two would cancel out. So that'll just be equal to x of 2. So I can manipulate this to prove this if someone didn't understand that was equal to x of 2, that those work out. It's really just definite integration. If I asked you, what are 3 different ways a definite integral with an integrand of velocity can be used? Oh, geez. I hate questions like this. Let's think. Part 3. So displacement, position, distance, travel. Down above. What are 3 different but mathematically equivalent expressions to find average velocity over time from A to B? Ooh. That's one. That's the average value of a function. How could I rewrite that differently? Well, I can rewrite this as, instead of v of t, I can write that as like x prime of t. I think this is what they're looking for. That'd be valid too. Because velocity and x prime of t are the same thing. And if this was okay, I could rewrite this as 1 over b minus a times x of b minus x of a. That's just by integrating this right here. Those would be some ways to write that differently. I mean, I'm just showing the math and showing how that works. Just kind of doing the math a little bit. I think that's what they're going for here. There's different ways you could have written that. I'm sure there's more ways too. So those are some ways I would think that you can write this.